Okay, folks. One announcement real quick, and that is you do not have to do the pre-lab for tomorrow's lab. Because we haven't gone over weak acid titrations, and therefore I don't want to have you trying to do the problems. Some of it would have been easy to do, but some of it wouldn't have been as easy to do without having gone over it. So, second announcement is this is worst case scenario test. So I'm going to go over what's going to be on your test Friday. Which we've actually already covered all of the information that is on this document. Okay. You need to be able to write, or basically you need to be able to write a reaction at equilibrium, either for an acid added to water or a base added to water. You need to be able to identify the acid, the base, the conjugate acid, and the conjugate base. You need to be able to determine the stronger acid for both a oxyacid, which is when you use the oxidation states, or for a binary acid. You will either be given a strong acid or you will be given a strong base. And you'll be asked to calculate the hydronium, the hydroxide, the pH, and the pOH. You'll either be given a weak acid or a weak base and asked to calculate the pH. You'll be asked to identify a Lewis acid and a Lewis base. You will be asked to determine, there are 4 of them, a salt, whether it's acidic, basic, or neutral. You will be given a weak acid, weak base reaction and asked which direction does the reaction proceed. For that, you will be given the diagram that I printed off for y'all to help you determine which direction the reaction proceeds. Finally, you'll be asked to determine the pH of a buffer solution and of a buffer solution that is disturbed. As far as equations you are given, and constants you are given the KW, you are given the Henderson-Hasselbalch equation, you are given 14 is equal to pH plus POH. You're given the pH is equal to negative log of hydronium, POH, negative log of hydroxide, pKa, negative log of Ka. And you're given your Kw is equal to Ka times Kb. In other words, let me double check, but I want to say the only equation that you are not given is Kw is equal to hydronium times hydroxide. Any questions? The test is 4 pages long.
Will tractations be on there? So tractations won't be on there?
What?
What we're going over in lab tomorrow?
We will not be, no, there will not be titrations on this one. It'll only occur on the next exam. Four pages seems short, but when it's mostly mathematical calculations, you still have to know what you're doing. Pretty much need to know what calculation to do when to get the correct answer in a decent amount of time. I don't expect the test to change much from what I just gave you. Basically, I'm deciding on whether it's going to be a weak acid or a weak base. I think the rest of what I have is a given, but I'm trying to decide on that one little piece.
What was the first thing that you were gonna give us? The first equation of constant. Yeah,
KW is equal to 1 times 10 to the minus 14. Mhm. Okay. There are a couple of I'm trying to make sure that I can. Whoops. Okay, so there are just a couple of things I wanted to go over with respect to buffers, which we started on Friday. So just as a reminder of the buffers and the calculations that we were doing on Friday, basically, again, you need to be able to both calculate a buffer and calculate a buffer after a stress is added. Now, as a reminder, you can continue using this concept of rice. Right, when we talk about R, you're going to write the acid dissociation reaction. In water. For the I, it will be the initial concentrations of the weak acid and its conjugate base. For C, that is going to be the change. And the key to this is you have to remember that acids react with bases. So if you're given an acid, it means you're going to lose that quantity of base in the buffer. If you're adding a base, it means you're going to lose that quantity of acid in the buffer. And then E does not stand for equilibrium in this case. We're just going to call it equals, where we add I and C together. Once you have your E value, then that's when you use the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the base in the buffer over the acid of the buffer. So that is just a kind of getting our brains going where I left off on Friday. What I want to describe is a couple of things about the buffers. So what is going to be the most effective buffer? The most effective buffer is really going to have two qualities about it. Quality number one is that the concentration of the acid is going to equal the concentration of the conjugate base. By your conjugate acid-base pair having equivalent concentrations, it's going to allow for the best it's going to allow it to be the most effective buffer it can be. The second factor is that you want the concentration of the acid and base to be high. Let's face it, the higher the concentration of that weak acid, the more sodium hydroxide you could add to the buffer and it not impact the pH. So those are two qualities that will make for an effective buffer. The second brief thing I want to mention is the buffer capacity. And the buffer capacity is described as the amount of acid or base that can be added to the buffer without altering the pH or without significantly altering the pH. The last thing I want to mention is the best buffer. The best buffer is going to be a weak acid conjugate base pair that has a pH as close to the desired, I'm sorry, has a pKa, not pH. Has a pKa as close to the desired pH as possible. So these are just a few factors when we choose a buffer. I mean, for the most part, we've been working problems dealing with buffers, but these are a few factors that go into choosing the correct buffer system. You want it to have a pKa as close to the desired pH as you can get it. You want it to be able to absorb as much strong acid or strong base as possible. So you want it to have a really good buffering capacity. And one thing that leads into that buffering capacity is that when you're developing the buffer system, you do so that the weak acid and conjugate base concentrations are as high as possible, and they are equivalent to one another. We will see a buffer. We will be creating buffers when we get into weak acid, strong base titrations, and weak base, strong acid titrations later in the week or next week. Which leads us to the next thing we're getting into. And that is titrations. And it is what you will be doing tomorrow. And it is what you did in College Chemistry 1. So in College Chemistry 1, if you'll recall, you had a burette that you filled with sodium hydroxide. That burette was inserted into an Erlenmeyer flask that contained oxalic acid dihydrate, and phenolphthalein, which was the indicator. Now, in College Chemistry 1, to our solution, we added sodium hydroxide until you obtained a pale pink endpoint. The endpoint is the point in the titration when you have exceeded the equivalence point by usually a half drop of titrate. Something else discussed in College Chemistry 1's laboratory was the equivalence point. The equivalence point is the point in the titration where you had stoichiometric amounts of acid and base. Everything I just described should be familiar. Now, what we don't do in College Chemistry 1 is we don't look at what the addition of every little bit of titrant does to the overall pH. We obtain the end point. We obtain the equivalence point, but we don't look at the titration. And tomorrow you are going to be looking at a titration. Now you're going to be doing a weak acid, strong base titration tomorrow, just like you did in College Chemistry 1. Today we are going to talk about strong acid, strong base titration. When you do a strong acid, strong base titration, what you're going to do is you're going to graph the volume of titrant versus the pH. Now, if you start out at a strong acid, what kind of pH would I expect for a strong acid? A high one or a low one? Low, because anything below 7 is acidic. So we're going to expect to start out at a very low pH. And that pH is going to slowly increase until it gets close to the equivalence point. Right around the equivalence point, we're going to see a significant increase, and then it's going to level back out. Now, if you're talking about a strong acid, strong base titration, then this equivalence point is going to occur at 7. That is because if you look at our strong acid, strong base, we have a proton donor, such as hydrochloric acid. We have a hydroxide donor, such as sodium hydroxide. And when those are combined in equivalent quantities, you're going to make water. and you're going to make sodium chloride. Now, at the equivalence point, remember, I said all that is present at the equivalence, excuse me, remember what I said is at the equivalence point, that is the point where every single bit of the acid is used up by base. It's the point where you have stoichiometric amounts of acid and base. So if you have stoichiometric amounts of acid and base, then at the equivalence point, all that is present is water and sodium chloride. Now think back to our salts. When you think back to the salts, this came from the sodium hydroxide, that came from the hydrochloric acid. We had a strong base, strong acid, and so the salt was neutral. Hence the reason we're talking about a pH of 7 is because we're talking about something that is completely neutral. Now, the document I passed out to you is a document that allows you to calculate the pH at various stages throughout the titration. Step number 1 should be to go back to college chemistry 1 and basically calculate what the equivalence point is. What is the stoichiometric amounts of reactants that are needed? Then we're going to take and develop something similar to an ice table for a strong acid, strong base. It's not quite an ice table, but it's similar. But we're going to have to take into account dilutions as we go. And then you got to think. You have to think about this diagram here and ask yourself, if this is what I'm taking my pH of, what is in here? At any given time. That's what that think means. Is ask yourself, what's there? Is it acid? Is it base? What is there? Is it a buffer? What's there? Okay, I'm a firm believer in doing an example to illustrate. And we're only going to get it started today. .0 milliliters of 0.100 molar hydrochloric acid is titrated with 0.200 molar sodium hydroxide. What is the pH of the initial solution after milliliters. Sodium hydroxide has been added. After 10 milliliters, sodium hydroxide has been added. After 12.5 milliliters has been added. And after 15 milliliters. Is added. Okay. Step number 1 is to basically come up with the reaction and to determine the equivalence point. The reaction we are looking at is hydrochloric acid reacts with sodium hydroxide. And the products are water and sodium chloride. Any questions so far? First thing we're going to do is figure out the equivalence point. We have 25.0 milliliters of HCl solution. And we're going to convert that into sodium hydroxide. The HCl, so there's 1,000 milliliters in 1 liter. The sodium hydroxide was 0.100 molar. I'm sorry, the HCl was 0.100 molar. According to the balanced chemical equation, for every 1 mole of HCl that reacts, you will need 1 mole of NaOH. And we were told that our sodium hydroxide was 0.200 molar. When you calculate that out, it should come out to be 0.0125. Yeah. So it comes out to be 0.0125 liters, or in other words, it is equal to 12.5 milliliters sodium hydroxide. Okay. This is where I want you to think. If we go back up to this information up above, we know that this is the equivalence point. At the equivalence point, the pH is always going to be the same as long as it's a strong acid, strong base. As long as it's a strong acid, strong base, the pH at the equivalence point is going to be 7. I didn't have to do a calculation for it. Because no matter what, as long as it's a strong acid, strong base, the pH is going to be 7. What I know is that up until that point, I'm going to have an acidic environment. And after that point, it's going to be a basic environment. So that's part of the thinking through this. Now, the initial pH. What do I have initially? Do I have acid? Do I have base? Do I have a combination thereof? You have acid. Do I have a strong acid or do I have a weak acid? Strong acid. We've been doing these problems, folks. I have a strong acid, and that strong acid is in water. That strong acid, because it is a strong acid, dissociates entirely to form hydronium and chloride. If I start out with 25, if I start out with a 0.100 molar HCl solution and it dissociates entirely, that means I'm losing all 0.100 of the HCl. I will gain 0.100 of the hydronium and gain 0.100 of the chloride. So when it's all said and done, there's no HCl. What there is 0.100 of the hydronium and 0.100 of the chloride. Your pH equals the negative log of the hydronium. So that's equal to the negative log of 0.100, which should equal 1, if I'm doing this in my head correctly. Yeah. Folks, that's because if you think about this flask at this point, all that was in this flask was the 0.100 HCl. We have, because this was the initial pH. This is pH before anything is added. Okay. Now, after 5 milliliters of base, at this point, you're going to have to do a dilution calculation. Because if you think about this flask here, you have 25 milliliters of hydrochloric acid. But to that, you've added 5 milliliters of sodium hydroxide. So in other words, you don't have 25 mils of, they're going to combine. So my new hydrochloric acid concentration This is where you gotta use M1V1 equals M2V2. You need to calculate M2 here by using M1V1 equals M2V2. Your initial molarity was 0.100. Your initial volume was 25 milliliters. Your final molarity is what you're calculating. Your final volume is 30 milliliters because we added 20 plus, or 25 plus 5 together. So our new concentration of our acid is 0.083. We can do the same thing for our base, our sodium hydroxide. It's M1V1 over is equal to M2V2. So that is 0.200 times 5.0 is equal to our second concentration times 30. Keying that in, that's 0.033. Yes. What now?
Where'd you get that equation from?
That is, anytime you're dealing with a dilution, that is the dilution calculation from College Chem 1. Now, at this point, we have hydrochloric acid reacting with our sodium hydroxide to form water and sodium chloride. We started out with 0.083 of our hydrochloric acid and 0.033 of our base. When you add a strong acid or a strong base, the reaction will go to completion. So whoever's in the lowest quantity is going to get used up. So in this case, we're using up 0.033 in our process, and what we have left is we have 0.05 molar of our acid and none of the base. So when we take our HCl, again, don't forget this is all occurring in water. So HCl reacts in the water to make hydronium plus Cl minus. If you start out with what you have is 0.05 molar of that, you're going to lose all 0.05 molar in the formation of 0.05 of the hydronium and 0.05 of the chloride. So our pH is equal to the negative log of the hydronium, which is equal to the negative log of 0.05, which is 1.5, I believe. No, 1.3. Yes. Go ahead.
So that the one that has the lowest concentration is the one that's going to be used up.
As long as there's a strong acid or a strong base involved, whoever's got the lowest concentration is getting used up. Okay. Don't panic. This isn't on the test. This is for next test. And we will be doing some more of these problems on Wednesday. So you'll become more familiar with it.